Now let's look at work. The basic equation for work is equal to force times distance. Now when you are moving an object and providing a force to the object is going to move a distance if the force is significant enough to actually cause the object to move. So if the object does move a distance and a force was provided on it, it took work to get the object to move. Now work, if we look at the units, force is in newtons and distance is in meters. So work is a newton meter. Now a newton meter has a special name. We call it a joule, and a joule is a form of energy. So work is a type of energy. It takes energy to do work. Well, force is equal to mass times acceleration. So if we substitute mass times acceleration in for force, we get that work is equal to MAD, and this is true in that everyone is usually mad when they have to do work. Okay.
LOL.
Now, let's look at a substitution for acceleration. Vf squared is equal to Vi squared plus 2AD. We just chose one of the linear equations, the 5 linear equations from the first unit that had an acceleration in it, and we're going to solve for acceleration and substitute into the work equation. Alright, so this becomes Vf squared minus Vi squared is equal to 2AD. And if we divide both sides by 2D, we get acceleration. And I'll just divide that and flip at the same time. So acceleration is going to be equal to Vf squared minus Vi squared divided by 2 times the distance that you traveled. Alright, now we take this, since acceleration is equal to this, we substitute this in for acceleration in the work equation. Work is equal to mass times Vf squared minus Vi squared over 2 times the distance traveled, and that's times distance. Your distances divide out, and I won't skip any steps, we'll just go straight through with this. Mass times Vf squared minus Vi squared over 2. If we factor the mass through to here, separate everything out, I'll go ahead and do a couple steps at once. This ends up being 1/2 mVf squared minus 1/2 mVi squared. Now 1/2 mVf squared, or 1/2 mv squared in general, is equal to kinetic energy. So kinetic energy is equal to 1/2 mass times velocity squared. So work is equal to final kinetic energy minus initial kinetic energy. That's equal to the change in kinetic energy. Now work is also equal to the change in the potential energy plus the change in the kinetic energy. And potential energy is equal to mass times gravity times height, and the basic equation for kinetic energy is 1/2 mv squared. And if we include the change of these, you could rewrite this as mg height final minus height initial plus 1/2 mvf squared minus 1/2 mvi squared. And that's equal to work. Now let's analyze the units for this really quickly to make sure that everything is still in joules. Let's look at potential energy. Okay, mass times gravity times height. Mass is in kilograms, gravity is an acceleration, it's a meter per second squared, and height is a distance, which is a meter, which makes that squared. So the unit, the base unit for mass times gravity times height is a kilogram meter squared per second squared. Now that needs to be equal to a joule, so we've got to figure out what force times a distance is equal to. Work is equal to force times distance, which is a newton meter. Well, a newton is a kilogram meter per second squared because it's a mass times an acceleration, and a newton times a meter would make that squared. So a newton meter, which is equal to a kilogram meter squared per second squared, is 1 joule. So potential energy is a unit of energy, so it's in joules. kilogram meter squared per second squared. And now kinetic energy. Let's look at 1/2 mass times velocity squared. Mass is kilograms, velocity is meter per second, and that's velocity squared, so that ends up being kilogram meter squared per second squared. And kinetic energy is also a unit of, well, obviously energy, so kilogram meter squared per second squared is also a joule. So essentially we have work, potential energy, and kinetic energy, all energies, and all measured in joules.